Determinant of a matrix of order 3, the concept of expansion. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we mastered the basics of finding the determinant for a 1x1 matrix and a 2x2 matrix. Now, as you might recall, calculating a 2x2 determinant is quite a straightforward process. It's simply the difference between two products, which you likely know as the cross-multiplication method. However, as we move into today's lesson, we are stepping up to a 3x3 matrix, and I must warn you, it is significantly more complex. You will find that you cannot simply apply that same cross-multiplication trick to a 3x3 matrix to get the answer. Instead, we need a more structured approach. Today, we are going to learn a specific mathematical process called expansion, which will allow us to break this larger problem down into something much more manageable. Understanding the concept of expansion. You can think of expansion as a divide and conquer strategy. It's a very powerful way to approach complex problems. Since we have already mastered how to calculate the determinant of a 2x2 matrix, our primary goal here is to use expansion to break down that large, intimidating 3x3 determinant into a series of smaller, more manageable 2x2 determinants. If we were to describe this more formally, we would say that expanding a determinant means expressing the determinant of a higher-order matrix as a linear combination of determinants of lower-order matrices. It sounds a bit technical, but it really just means we are rewriting one big problem as a sum of smaller, simpler ones. To make this even clearer, let's use a real-world analogy. Imagine you have been appointed as a project manager, and you've been assigned a massive, high-stakes project. This large project is like our 3x3 determinant. It's simply too big to tackle all at once. To ensure success, you decide to break this massive project down into 3 smaller, manageable subtasks. These subtasks are like our 2x2 determinants. Once you have successfully completed each of those 3 subtasks and combined their individual results, you have effectively completed the entire overall project. Now that we've established that a 3x3 matrix is too complex to solve with a simple cross-multiplication like we did with the 2x2 matrices in the previous section, let's look at the core concept behind our new method, expansion. In the next slide, I will show you the specific, step-by-step process of how we actually perform this breakdown in a matrix. The general process of expansion. Now that we understand the divide and conquer philosophy from the previous slide, let's walk through the actual, step-by-step procedure for performing this expansion. There are 4 main stages you need to follow. First, we have step 1, selection. You have complete freedom here. You can choose any single row or any single column from your 3x3 matrix to work with. Once you've made your choice, we refer to this as your row or column of expansion. Next, we move to step 2, reduction, which is how we create what we call minors. This is the core of the process. For every element you've picked in your chosen row or column, I want you to mentally or physically hide or delete the entire row and the entire column where that specific element lives. Once those are gone, you'll see that the remaining elements form a smaller 2x2 matrix. The determinant of this smaller matrix is directly linked to the element you originally selected. Step 3 is multiplication. Now, you simply take the element from your original 3x3 matrix and multiply it by the determinant of the 2x2 matrix you just created. Finally, we reach step 4, summation. This is where we bring everything back together. You will add or subtract these individual products to reach your final answer. Just a quick heads up, you'll need to follow a specific sign convention, which we will discuss in detail shortly, to decide whether to add or subtract each term. Once you've combined them all, you'll arrive at the final scalar value, which is the determinant of your original 3x3 matrix. In the next slide, you'll see how this process gives you a lot of flexibility in how you approach a problem. Flexibility of expansion. Now, before we jump into a concrete example, I want to highlight a very powerful property of determinants that you should keep in mind. One of the most important properties of determinants is that the final result is completely independent of the row or column you choose for your expansion. Think about what this means. It doesn't matter if you decide to expand along row 1, row 2, or row 3. Similarly, it doesn't matter if you choose to expand along column 1, column 2, or column 3. No matter which path you take, the resulting value of the determinant will always be exactly the same. This flexibility is incredibly useful in practice. It allows you to be strategic. You can look at your matrix and choose the specific row or column that contains the simplest numbers, like zeros, to make your calculations much easier and faster. In the next slide, we will see this principle in action with a step-by-step numerical example. Illustrative example. Now that we have understood the theory behind expansion, let us put it into practice with a concrete example. Let us consider a matrix, which we will call A, and find its determinant by expanding along the first row. Our matrix A is a 3x3 matrix, where the first row contains the elements 2, 3, and 1. The second row contains 0, 4, and 5, and the third row contains 1, 2, and 6. We denote the determinant of using vertical bars around the matrix. Let's walk through the step-by-step expansion along the first row. Step 1, we begin by focusing on the first element of the first row, which is a sub 1, 1 equal to 2. Following the reduction process we discussed in the previous slide, we will delete the first row and the first column. The remaining elements form a smaller 2x2 determinant consisting of 4, 5, 2, and 6. Therefore, our first term is 2 multiplied by the determinant of this 2x2 matrix. Step 2, next we focus on the second element of the first row, which is a sub 1, 2 equal to 3. Again, we delete the first row and the second column. The remaining elements give us a 2x2 determinant of 0, 5, 1, and 6. However, please pay close attention here. As we will highlight later in our discussion on common mistakes, the sign for this position changes. So our second term is negative 3 multiplied by this 2x2 determinant. Step 3, now we focus on the third element of the first row, which is a sub 1, 3 equal to 1. We delete the first row and the third column, leaving us with a 2x2 determinant of 0, 4, 1, and 2. This gives us our third term, 1 multiplied by this 2x2 determinant. Step 4, finally, we combine all these results into a single expression. The determinant of A equals 2 times the determinant of the first minor, minus 3 times the determinant of the second minor, plus 1 times the determinant of the third minor. Now let us perform the actual arithmetic to find the final value. For the first part, we calculate 4 times 6 minus 5 times 2, which is 24 minus 10, resulting in 14. For the second part, we calculate 0 times 6 minus 5 times 1, which is 0 minus 5, resulting in negative 5. For the third part, we calculate 0 times 2 minus 4 times 1, which is 0 minus 4, resulting in negative 4. Plugging these back into our expression, we get 2 times 14, minus 3 times negative 5, plus 1 times negative 4. This simplifies to 28 plus 15 minus 4. Adding 28 and 15 gives us 43, and subtracting 4 leaves us with a final determinant value of 39. Key takeaways. First, remember that expansion is not just a random calculation, but a systematic process of reducing a 3x3 determinant into a sum of several 2x2 determinants. We are essentially breaking a complex problem down into smaller, more manageable pieces. Second, keep in mind the incredible flexibility you have. You can choose any row or any column to perform your expansion. Whether you pick the first row, the third column, or any other, the final result will always remain the same. This is a powerful tool because, as we saw in our example, choosing a row or column with simpler numbers can save you a lot of work. Finally, always remember the core mechanic of the process. You must multiply each selected element by the determinant of the smaller matrix that remains after you have removed that specific element's row and column. All right, let's take a moment to recap the essential points we've covered today so you can consolidate your understanding. Now, before we move on, I want to highlight a few common pitfalls where students often lose marks, so please pay close attention to the next slide. Common mistakes. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. As we've seen through our expansion process, there are several places where a small slip-up can lead to a completely wrong answer. First, let's talk about incorrect minor selection. This is a very frequent mistake. When you are focusing on a specific element, you are supposed to hide or delete its corresponding row and column. However, students often accidentally include numbers from that deleted row or column when writing down their new, smaller matrix. To prevent this, I highly recommend that you physically cross out the row and column with your pencil, or at least do it very clearly in your mind, before you even attempt to write the 2x2 matrix. Second, and perhaps most importantly, is ignoring the sign. It is incredibly easy to treat every term as a positive number, but as we saw in our worked example with matrix A, the signs actually alternate. For the first row, the pattern follows plus, minus, plus. If you forget to flip that sign for the second element, your entire calculation will be off. Now, don't worry if the logic behind why the signs change isn't fully clear yet. We will be covering the detailed sign convention in our very next subsection. Finally, watch out for calculation errors in the 2x2 determinants. Remember, calculating a 3x3 determinant isn't just one calculation. It is actually 3 separate 2x2 calculations bundled together. If you make just one tiny arithmetic error in a single minor, especially when performing the subtraction step, it will cascade through your work and lead to an incorrect final result. So, please, take your time and double-check your subtractions in each step. Stay vigilant, and you'll master this concept in no time.